proceed with the talk.
Yeah, thank you for the introduction and the opportunity to talk in this excellent conference. So today I'd like, I'm sorry, I am Takuya Okazaki from Kogakuin University and Meiji University. So today I'd like to talk about hydrothermal selective leaching of lithium from lithium cobalt oxide and the CO2 atmosphere. So as you know, lithium-ion batteries has many advantages, including high energy density, long cycle life, large capacity, and lightweight. So as you know, the LIBs have applied so many devices, laptop, phones, and electric vehicles. So it is expected to increase demand for LIBs. So the amount of spent LIBs also will also increase with growing LIBs demand. So developing technologies to recover metals from LIBs at low cost and with low environmental impact is crucial. So there is recovery of metals. So we know there are cathode materials of LIBs, LCO, lithium cobalt, LMO, LFP. So we focus LCO. This has some precious metals, lithium cobalt. In the general wet process, spent LIBs is treated by strong chemicals, for example, acid or alkaline, to dissolve its metals in the water. So, and then these metals sediment to solid. Recently, hydrothermal process is reported for leaching metals in acid water. The hydrothermal process has higher ionic product than under ambient conditions. So this method has some advantages such as fast reaction rate and reduced chemical consumption. There are previous studies on hydrothermal acid leaching for LCO like this table. So some acids are used, including sulfuric acid, nitric acid, citric acid, something, etc. So and then leaching rate are like this. So the high leaching rate of lithium and cobalt using inorganic and organic acids are achieved by the hydrothermal process. So we are inorganic acid is low cost acid, but this acid has disadvantage. It is closed equipment by the strong effect. But organic acid is weak acid, but this has higher cost as compared with inorganic acid. In both cases, the separation of lithium and cobalt is required after leaching. Yes, in both acid, inorganic acid, organic acid. So we focus carbonate acid. This is low cost and weak acid. Yeah. So there is equilibrium of carbonate. The pKa1 is 6.37. It is weak acid. So carbonate is easily obtained from the CO2 in purging the water. So this graph showing the property of CO2 under the high pressure and high temperature. As you know, in short, the solubility of CO2 water, CO2 in water increasing and high temperature and high pressure. In this study, a method for selectively leaching lithium from LCO and hydrothermal conditions with high pressure CO2 was proposed by our research result. There is experiment. This is hydrothermal reaction equipment. So chemicals in autoclave LCO. This is reagent grade of LCO and water and solid CO2. We in this study. Oh, I'm sorry. So in this study, we use solid CO2. Uh, Dry ice is used in this study. So conditions is like this: temperature, reaction time, and pressure. After the hydrothermal process, the mixture is separated to liquid and solid. Lithium and cobalt in liquid is analyzed by ICP-AES and solid is analyzed by the powder XRD. First, we investigate the effect of reaction temperature. Left graph showing the leaching rate of lithium and cobalt. So you can see the blue line. So lithium leaching rate increased with temperature. So no cobalt was detected by the ICP-AES. So the limit of detection was 0.8 milligram per liter in this in our dilution condition. So next graph showing the with and without CO2 condition. So you can see the bar graph. So higher reaching rate of lithium and lower cobalt will be decrease like this without CO2. So selective leaching of lithium from LCO was achieved by the hydrothermal reaction in the presence of CO2. There is an XRD results. So at reaction temperature 100, 200 degrees Celsius, LCO is observed. This is also almost similar reagent LCO. And then at 225 degrees Celsius, LCO and cobalt hydroxide is observed. And then 250 degrees Celsius LCO, the cobalt hydroxide and cobalt oxide is observed like this. So as temperature increased, LCO transform into cobalt hydroxide and subsequently cobalt oxide was formed. Next, we try the investigation of effect of reaction temperature. Left graph showing the effect of reaction pressure. So you can see the as pressure increases, lithium leaching rate was increases to about 90%, and the cobalt was not detected, so less than 0.8 milligram per liter. So, so XRD analysis showing the almost the same peaks, but something different was crystallinity of reagent LiCoO. Next, next is effect of solid liquid ratio. This graph also showing the effect of solid liquid ratio. 1 and 10 was almost the same level, but at 100 gram per liter, the leaching rate was decreased. So XRD analysis showing the at 100 gram per liter, the LiCoO reagent LiCoO was remaining like this. So it is due to the reduced exposure to water, and so much LiCoO not react with acid. Next, we investigated reaction time. So the reaction time at 6 and 12 hours, almost the same level, but 3 was something low. So reaction time of 6 hours is sufficient, but we observe the XRD analysis. So something different. The first peak, this LiCoO peak, so it indicating further heating reduces crystallinity of remaining LiCoO. So there is a discussion for the reaction mechanism. So first, lithium from LiCoO ion exchanges with proton to form cobalt hydroxide. So there is reported in low concentration acid solution, hydrothermal reaction converts LiCoO to cobalt hydroxide. It meaning LiCoO to HCO. So these are similar layered crystal structure like this. In our experiment, carbonate in water contributed as a source of weak acid, so it is protons. So next, at temperature higher than 225 degrees Celsius, thermal decomposition of cobalt hydroxide to cobalt oxide is occur like this. So this reaction, something reported some researcher in ambient condition, but so this is not a hydrothermal process, but we believe it also same Yeah, also same. This hydro thermal decomposition makes cobalt oxide. There is summary hydrothermal reaction and the presence of solid CO2 selectivity leach lithium into water. So cobalt ox hydroxide, cobalt ox hydroxide and cobalt oxide were absorbed in the products. It is due to representing the intermediated and final products, respectively. So you can see, the experimental condition is something tough. So high pressure and high temperature. So in future research, we will reduce the extreme pressure and temperature in hydrothermal condition. So next we try to other materials. So just we tried LCO reagent LCO. We will try to black mass some or some different cathode materials. So that's all. Thank you very much.
Okay, thank you very much, Professor Okazaki. So the forum is now open for question. Is there any question? If so, please raise your hand. Okay, actually, I have very quick question on the lithium ion you got it will be leached out and remain as a solution, right, in your from the hydrothermal process, right?
Yeah.
Okay, and if we replace LCO with NMC, right, in case that we want to use it for NMC, do you think that your method still work, or is there any other concern, or do you think it's gonna leach out some other metals instead?
Yeah, you're talking other material of LCO. You're talking.
Is that we want to use the same technique with other materials such as NMC, where we have nickel, cobalt, manganese oxide. It's
So
gonna work as well, or is there any other
yeah,
concern?
in my opinion, so it is works good, but now I'm not trying different materials, cathode materials. So just fundamental trying. First, we choose the LCO. So so very important question. So it is very important to try to something materials. So I have something concern. So it is in the case of LFP, so this required something oxidant. So, but this method has no oxidant in this experimental chemicals. So this is something issue in our experiment.
Okay, thank you so much, Professor Okazaki. So in if there is no, okay, very quick question, please.
Okay, I have just a little question. Like, you use like solid copper, solid carbon dioxide, like solid phase. Can we use like gas phase or liquid phase of carbon dioxide?
Yeah, it is very easy, but liquid carbon dioxide makes the pressure upper pressure is 5 megapascal something, but the advantages of use of solid CO2 can make the higher pressure than 5 megapascal. So it is so for this purpose we use solid CO2.
Okay, so thank you very much, Professor.
Thank you very much.
Okay, thank you. Let's thank the speaker again.